Rudewright Academy. Learn it, teach it, remember it. A graph is not a picture, it's a relationship. Think of it as a set of things and the connections between some pairs of them. That's the whole idea. And you already think this way every single day. Picture the people you know. Draw a line between any two who know each other. That tangle of dots and lines, that's a graph. One person off on their own is a stranger. And the very same shape shows up everywhere. Cities joined by roads. Web pages linked together. One shape, endless disguises. So we name its two pieces, and these two names are the whole foundation. A dot is a vertex, the thing. A line is an edge, the connection. You'll also hear vertices called nodes and edges called links. A graph is just a set of vertices and a set of edges joining pairs of them. Let me draw a small graph we'll keep in front of us the whole time. 5 places numbered 1 through 5. And 5 roads. 1 to 2, 1 to 3, and 2 to 3, which closes a little triangle. Then 3 reaches out to 4, and 4 out to 5. Place 5 is the loner, only touching 4. Whenever I say the graph, I mean this exact one. Here's the first big question that splits every graph. Do the edges point or not? A road you drive both ways, like a friendship, a handshake, has no arrowhead. The graph is undirected. But some connections go just one way. You follow a celebrity who's never heard of you. A one-way street. A prerequisite course. Those carry an arrowhead and the graph is directed. Here's the second question. Do the edges carry a number, or are they all the same? Right now, a road just exists, connected yes or no. That's unweighted. But real roads have lengths, tolls, time. Give each edge a number, its weight. Now you can ask richer questions. Not just can I reach a place, but what's the cheapest way? The weight might be distance, time, cost, or even a relationship strength. These two questions multiply together into 4 kinds of graphs. Undirected and unweighted, that's our plain town. Directed and unweighted, a follows network. Undirected and weighted, a roadmap with distances. And directed and weighted, one-way streets with travel times. That's exactly the shape behind every routing app you've ever used. One more word and it's the first number you can read straight off the picture. The degree of a vertex is how many edges touch it. Place 1 touches 2 roads. Place 2 touches 2. Place 3 is the busy hub with 3. Place 4 touches 2. And place 5, the loner, touches just 1. High degree means a hub, important and fragile. Now add those degrees up. 2, 2, 3, 2, 1. That's 10, exactly twice the number of roads. No coincidence. Every edge has 2 ends, so it adds 1 to the degree at each end. 2 in all. The sum of the degrees is always twice the edges. For directed graphs, we split it, arrows in and arrows out, counted separately. Now comes the hard part the rest of this lesson exists to solve. You can look at this picture and answer instantly. Is 1 connected to 4? Who are 3's neighbors? But a computer doesn't see pictures. It has only numbers in memory. So how do we write down which things connect to which, fast? There's more than one good answer. And they're genuinely different. The first way is the one you'd invent yourself. For each vertex, write down a list of its neighbors. 1 connects to 2 and 3. 2 connects to 1 and 3. 3 reaches 1, 2, 4. 4 to 3 and 5. 5 to 4. And notice, because the graph is undirected, every road shows up twice. The road between 1 and 2 puts a 2 in 1's row and a 1 in 2's row. 2 questions split the behavior. Who are 3's neighbors? Trivial. Go to row 3 and read it. 1, 2, 4. You touch exactly what exists. But second is 2 connected to 4. Now there's work. You scan row 2 looking for a 4. 1. No. 3. No. End of row. No 4. Tiny here, but 1,000 neighbors would mean scanning 1,000. The list stores only what exists, so on a sparse graph it stays wonderfully lean. The second way flips the approach. Build a grid with a slot for every possible pair. Write a 1 for yes and a 0 for no. 5 places, so a 5 by 5 grid. Row I, column J answers one question: is there an edge from I to J? Fill it off the same picture. Every road lights 2 mirrored slots. Everything else is a 0. 2 things make this grid tick. The diagonal is all zeros, no place has a road to itself. And the grid is a mirror. 1 connects to 2 and 2 connects to 1, the same fact recorded twice. Now the questions flip. Is 2 connected to 4? Instant. 1 lookup, row 2, column 4, 0. But who are 3's neighbors? Slow. You must walk the whole row. And the cost, 5 places, 25 slots. Only 10 ones, 15 dead weight. Double the places and the grid quadruples. 1,000,000 places wants 1,000,000,000,000 slots. It simply won't fit. Side by side, the trade-off snaps into focus. The list stores only what exists. It makes neighbors trivial, and it grows with the edges. But a pair check means scanning. The matrix reserves every pair. It makes a pair check instant, and it grows with the vertices squared. Mirror images, each fast at exactly what the other is slow at. So how do you choose? First, sparse or dense. A roadmap is sparse. A city touches a handful of others, never a million. The matrix's wasted zeros are fine when the graph is dense but ruinous when it's sparse. And most real graphs are huge and sparse. So the list is the default. A fully connected graph is dense, and there the matrix earns its keep. Second, what do you ask most? Walking a vertex out to its neighbors favors the list. Poking at random pairs favors the matrix. Match the choice to the shape and the questions. Now the skill that makes this useful, pulling the graph out of something messy. Take a social network. A vertex is a person. An edge is a connection. Friends, mutual, is undirected. Follows, one way is directed. Plain is unweighted, but interaction strength would be weighted. A person's degree is their popularity. Huge and sparse, so store it as a list. A roadmap for a navigation app. A vertex is an intersection. An edge is a road. One-way streets exist, so it's directed. Each road has a length or a travel time, so it's weighted. The directed and weighted corner, the richest one. Exactly the shape that finding the shortest route runs on. Huge and sparse again, so again, a list. Course prerequisites. A vertex is a course. An edge says you must take this one before that one. That has a strict direction and cannot reverse. So it's directed and unweighted. And the question, what order can I take these in, is a graph question about exactly this structure, finding a valid execution order. Feel the pattern in all 3. Find the things, the vertices. Find the connections, the edges. Then ask the 3 questions: directed, weighted, sparse, or dense. Those 4 moves turn any tangled real problem into a clean graph. A graph you can store and reason about. A handful of traps catch almost everyone. First, forgetting an undirected edge goes in twice. Record it once, and you've silently made a one-way road. Second, reaching for the matrix on a giant sparse graph. It wants 1,000,000,000,000 slots and won't fit. Third, confusing a vertex value with its position. Keep a name-to-index map. And fourth, believing the drawing is the graph. It's only a picture. The same graph can be drawn 100 ways. The deepest skill is noticing a graph when nothing says the word. Run a quick check. Are there distinct things? Those are your vertices. Is there a pairwise relationship between some of them? That's your edges. If both fire, you're looking at a graph. A maze is a graph. Cells are vertices. Can you step between these two? That's an edge. A word ladder is a graph. Words are vertices. Differ by one letter. That's an edge. Model it as a graph, and you're most of the way to solving it. So, the one model to keep. A graph is things and the connections between pairs of them. Read every one along three axes, directed or not, weighted or not, sparse or dense. And store it one of two ways. A list, lean, sized by edges and neighbors are trivial. A matrix, bulky, sized by vertices squared, and pairs are instant. Find the dots, find the lines, name the three axes, choose how to store it. That is the whole foundation. Want to keep learning? Come find us at academy.rudewrite.com.